students. Today we will continue the next article in this unit first, that is Davission and Germer experiment. This lecture will include the following points for the discussion. The first one is introduction about the experiment. Second, the schematic diagram of Davission and Germer experiment. Next, experimental setup. Next, the theory of diffraction of the electron beam from the nickel crystal. And finally, we discuss the results of the Davission and Germer experiment. Now, firstly, we discuss the introduction about the Davission and the Germer experiment. In earlier lecture, we learnt about the de Broglie hypothesis. According to de Broglie hypothesis, the electron can be reflected or diffracted, so they must be in the form of the waves. We know the physical phenomena which satisfy the integer rule. These phenomena are explained on the basis of wave nature. For example, reflection, refraction, diffraction, interference, and thus here the electrons are diffracted by the solid just like the X-ray, and therefore electrons satisfy wave nature, and that concept was explained here by de Broglie. The first experimental evidence of the matter wave was given by Davission and Germer in 1927, and in the same year by G.P. Thomson in England. They also succeeded in measuring de Broglie wavelength associated with the electrons. Now see here, this Davission and the Germer experimentally observed that the electrons were diffracted from the nickel crystal and confirmed the wave nature of the electron. And due to this work, Davission got a Nobel Prize in 1937. Now we see here the schematic diagram of Davission-Germer experiment. This arrangement, experimental setup of Davission and this Germer here, this experiment, which consists of mostly the three important here this part. The first one is the electron gun. That electron gun, which consists of the electrostatic accelerator. This is this accelerating voltage. Next one is the filament, tungsten filament. And the third one, we see here, this is a collimator. These three terms combined together, it forms electric gun. Second important here this term in this experiment is target, and that target used here is a single nickel crystal. Third is the electron detector. That electron detector is known as Faraday cylinder. This all that here is constructed here these terms, we have to explain one by one here. The experimental setup hold that assembly which is evacuated in a vacuum chamber. This reason is that deflection and the scattering of the electron by the mediums are prevented due to the vacuum chamber. Here it's short. Here this diagram we just see here, this is the filament. The same here this diagram we simplified just like here. The filament which gets heated by this potential here, small v. Therefore the filament gets heated, and due to thermionic emission the electrons are emitted. These electrons gets accelerated by using this electrostatic accelerator, particle accelerator. This voltage, if we apply the potential difference between the filament is to be goes on increasing, the electron gain more and more energy, and due to that one the energy of the electron goes on increasing. Such a accelerated electrons are passing through here the collimator which consists of the number of slits here. This fine electron beam gets sharp after passing through this narrow window of this collimator. Such a highly accelerated, fine and sharp here this beam which is targeted towards the nickel crystal. Here the nickel crystal is rotated about an axis and it is in the path of the electron here this beam here. When the electrons targeted to the nickel crystal, then that nickel crystal which acts as a grating, and therefore these electrons to be gets deflected or they get scattered towards this collector. That collector which named earlier, it is a Faraday cylinder. It is a double walled here this chamber. The retarding potential which is maintained between the two walls, since the Faraday cylinder is a double walled with perfect insulation from each other, and it is maintained at the retarding potential such that the high energy electron only enter into that heavy cylinder, and the slow electrons, these electrons once collide with the atom, its energy to be loses, that electron we call the slow electrons. These are rejected by that here this Faraday cylinder. Such a scattered electron beam is collected by this collector, and it measures the collector current, collector which measure the current. That current is a measure of intensity of the electron beam, and that detector is movable only in the angle between 20 degree to 90 degree. Such a scattered electron beam with fixed energy gets varied with the different angle here this phi. Phi is the scattering angle between the incident beam and the scattered electron here this beam. Means phi is measured with respect to the direction of the incident here this beam. Here this diagram is same. We simplified here. The filament which gets heated, it due to the red hot, it emits the electron. That electrons gain some energy using this electrostatic particle accelerator, and this fast accelerated electron beam, once it passes through the number of slits, it becomes fine and narrow. Such a accelerated electron beam is targeted on the surface of the nickel crystal. That nickel crystal will be composed of number of atoms. These atoms are arranged in very regular manner. All atoms are in ordered position, and due to that one, the number of atomic layers we just take into consideration. The electron beam also scattered in these different layers, and all the scattered electron beams, when these are in the phase, is correct. That is, we just say here it is a collector which collect, and we can get the constructive here this interference. That point we discuss in the next point. Now see here this experimental setup that, as we discussed earlier, it consists of the three important here these parts. The first one is the electron gun. That is, first one is the tungsten filament. Second is the electrostatic particle accelerator, and third one is the collimator. Second is the target. The target used as a single crystal of the nickel. Third one is the electron detector. That is also known as a Faraday Head cylinder. That we point discussed earlier. Experimental setup, whole that here this setup which is enclosed in a vacuum chamber. Thus the deflection and the scattering of the electron by the medium are prevented. These main points. Setup, electron gun, again it consists the same as one. All that point we just discussed earlier. See the tungsten filament, electrostatic particle accelerator, collimator. The target is a single nickel crystal. The electron beam is just say here fired normally to on this nickel crystal. The crystal is placed such that it can be rotated about the fixed axis. Here is the electron detector, also known as the Faraday cylinder. It is a double walled with perfect insulation and maintained at the retarding potential. Detector is used to capture the scattered electron from nickel crystal, which measure the intensity of the electron beam. Detector can be moved in a semi-circular arc with varied angle between 20 degree to 90 degree. Then we discuss about the theory of diffraction of the electron beam from nickel crystal. Now these are the construction of the Bragg's diffraction by using the nickel crystal. Here the figure shows here. This is the nickel crystal which composed of the number of atoms. All the atoms are arranged in the regular manner. Now we have to choose this set of the parallel planes. These are the set of the parallel here, the planes here. The separation between the two parallel plane is small d, and distance between the two nearest neighboring atom, that we call the capital D here. Here, this is the incident beam which is coming from the particle accelerator and the filament, which is targeted on the surface of the nickel crystal. That here this beam penetrate the nickel crystal through the number of the planes here. Now what happened here, if it is incident on the nickel crystal on the particular here the plane, it get scattered. This is the intense reflected here this beam here. Therefore it makes some angle. That angle we call scattering angle here, this phi, and it is the phi is the angle between the direction of the incident beam to the scattered electron here this beam. That here the phi is different, or this is varied using this movable here this detector collector here. Now we split this phi, the angle between the incident beam, and this is the normal drawn to that plane. This normal is exactly at the 90 degree. That angle we call here this alpha. Similarly, normal to the scattered electron beam, same angle we will choose here. This is to be alpha here. Now see here, we have to write the another here this angle between the direction of the incident beam with this plane. That angle we call here this theta, small theta, and that here the theta we have to calculate from the geometry, as well as this alpha, that also we have to find using this geometry of that here this figure. Now actually what happening here, that we see here, this is one of the plane of the nickel crystal. All the atoms are arranged in the periodic manner. We have to considering the separation between the two nearest neighbor atom, that is the capital D. This is the same we just writing here. Here the incident here is beam, electron beam, which is in the form of a plane in this wavefront, incident on the nickel atom, then it get here this scattered. Similarly, the another electron beam, it also gets here this scattered, and the scattered two electron, the scattered electron here the beam gets interfere, and due to the interference we get constructive and destructive pattern. Now when we get the constructive, if the incident here this beam, electron beam, which is in the phase same as the scattering electron beam, which is also in the phase, both are in the phase here, and therefore we get this scattered electron here this beam, which satisfy the constructive here this pattern. Here we have to find the geometry. Now what is the sign alpha? Here the alpha we measure earlier, it is the angle between the incident beam and the normal drawn to this plane, that angle is alpha. Similarly here is the plane of this atom, and we can just draw here, this is the inclined the planes here, that angle is same here. This is the small alpha. That here this alpha from this cone, we have to finding here sin alpha is equal to d is the separation between the two atomic plane small d divided by distance between the two nearest neighboring atom of the nickel crystal, that is the capital D. Secondly, we have to find the theta. This is the Bragg's angle theta. How we find here? Theta, we know that the normal drawn to the plane, this is exactly 90 degree. Here from atomic plane to the direction of the incident beam, that angle is theta. If the 90 degree minus alpha, it gives theta. Therefore, we write the Bragg's diffraction angle theta is equal to pi by 2 minus alpha. Here, in this experiment, we get the maximum constructive pattern which occurred at angle alpha, that is to be equal to 25 plus 25, total angle is to be phi. That phi we write here 50 degree. Here, this is the phi. Hence, the Bragg's diffraction angle for the prominent, here this case, we mention only here, theta equal to pi by 2 minus alpha, that equal to 90 minus 25 equal to 65 degree. Since these terms we use to explain the theory for diffraction of the electron. Now, here we get the various polar graphs are to be plotted here. How we plot the polar graph? We know here the accelerating potential, for different accelerating potential, we get the energy of the electron to be fixed for the particular accelerating voltage. That electron gets, high energy electron gets scattered from the nickel crystal and it is collected by this collector. The collector is moving in between the angle 20 degree to 90 degree. Therefore, for different values of phi and fixed value of the accelerating potential, we get the various polar graphs. These graphs are shown here. Here is the single nickel crystal. That single nickel crystal to be rotated about an axis. That single crystal, one of the plane is in the normally to the direction of the incident here, this beam. Then what happened? This incident beam to be get scattered in different direction. We can just say here that angle is different. We have to start from 0. Here angle we write 30 degree. We write here the 60 degree and this is the 90 degree. Here what happening here, at higher angle, the scattered electron beam intensity is lower. It goes on increasing and the nature of the graph is very smooth here. That graph is plotted at the accelerating potential 36 volt. Now, if this accelerating voltage goes on increasing from 40 volt to 66 volt, we get the various polar graphs. That here the polar graph, the first here this polar graph is 36 here, this one. Second one is the 40 volt. It again show smooth curve here. But as the voltage goes on increasing, then what happening here? A small bump which is appeared on this graph, it becomes maximum, then the intensity becomes minimum, and then it goes on decreasing here. Similarly, the third one at 48 volt, what it shows here, a small bump which is appeared in this polar graph, it slightly goes on increasing, and we get the prominent here, this bump which is appeared at 54 volt, and where the intensity of the scattered electron beam reaches maximum, we draw a line from this origin. It measures the intensity of the electron here, this beam, and that is the maximum. Again, voltage increase, then this bump, its intensity goes on decreasing, and finally it vanishes at the higher potential difference, 66 volt. Now what it shows here, we have to just writing the prominent here, this peak which is appeared at 54 volt. That graph we have to plotting here. The polar graph of the scattered intensity versus the scattering angle theta for 54 volt. Now this is the one of the diagram, we enlarging that one. Here the scattering electron intensity, which is we just take on that here this axis, and here the angle is to be varied. That angle is varied from 0 to 30 degree, 60 degree, and here it is 90 degree. Now what it shows here, as the incident beam is targeted at the nickel crystal and at the higher angle, its intensity, it goes on increasing, it becomes maximum. Therefore, this is the maximum intensity here. After all, as the angle goes on decreasing, intensity, it goes on decreasing, it becomes minimum, and then it slightly increases. Now the same behavior is here. We have to just draw here. Hence, from that here this curve, we show here, this is the prominent bump which is appeared on that here this graph. Here, from this figure 1, we have to draw earlier. Now how we find the Bragg's angle of diffraction theta? This is the 90 degree minus alpha, and this is the 65 degree. Also the lattice spacing between the two planes in a nickel crystal, that we have to denote by small d, and distance between the two nearest neighboring atom, that we know the capital D. Then we get the sin alpha is equal to small d by capital D. Here for nickel crystal, the distance between the center of the two neighboring atoms is constant, 2.15 angstrom. Therefore, we separate the small d term. Spacing between the two planes, d is equal to capital D sin alpha. D is 2.15 sin here this alpha, since total scattering angle phi in between incident beam and the scattered beam, we write here the alpha plus alpha. Therefore, this alpha is to be 25, since phi is 50 degree for that prominent peak here. Therefore, we write here this 0.909 angstrom. Here we write the Bragg's condition for first order only, that is n equal to 1. The condition becomes n lambda is equal to 2d sine theta, where n is 1. Therefore, simply write the lambda equal to 2d sine theta, or 2 multiplied by 0.909 into sine theta. That theta we have to find here. This is the 65 degree, and the resulting wavelength of the electron in this beam from the experimental result we get 1.65 angstrom. Therefore, this gives the experimental result for lambda associated with the electron. Next, we calculate the theoretical result for the wavelength of the electron. For theoretical calculation, we use the prominent peak where we get, and that voltage is 54 volt. Therefore, using the equation we have to derive earlier, that point we discussed earlier, the wavelength of the electron, we have to simply calculating here the h divided by under root twice m ev. Since this is a simplified form of the h by p, p is the momentum of the electron that we find earlier. Substitute all the values. 6.6 into 10 raised to minus 34 divided by under root 2 into 9.1 into 10 raised to minus 31 into 1.6 into 10 raised to minus 19. This is the charge on this electron, and V, this is the potential 54 volt. Now simplify all the terms, numerator and denominator. We get the result, the wavelength of the electron, by using this theoretical formula, lambda is equal to 1.67 angstrom. Therefore, what it suggests here, what are the results for the Davission-Germer experiment? The first one is the distribution of the electron is measured as a function of scattering angle phi, since that phi is varied for fixed electron energy. Secondly, the strong scattered electron beam is detected only at the accelerating potential V equal to 54 volt, and corresponding angle, scattering angle, we get it to be 50 degree. Now for that strong scattering electron beam, actually how it vary? It gives the intensity of the electron beam, which is varied with respect to here the scattering angle phi, and that we just see here at the higher angle, that is below 90, intensity slightly increases, it becomes maximum, and then it goes on decreasing, it becomes minimum and slightly increase here. This shows that the occurrence of maxima and here this minima is due to diffraction of the matter wave associated with the electron. Thus, diffraction phenomena which arises due to the scattering of electron wave. As we writing here, just say this is the sharp peak from that here this graph we have to note here. This is the maxima, this is the minima. Electron gets diffracted by the atom on the surface of the metal as though the electrons are acting as like a wave here. Secondly, the observed and theoretical value of the lambda that we find earlier. The observed wavelength of the electron, that is from the experimental result, it is 1.65 angstrom, and the theoretical wavelength of the electron using the lambda equal to h divided by under root twice m ev, this is 1.67. This both here the results are in good agreement with each other. Theoretical and experimental results are same, and therefore it confirms that the electron which exhibit wave nature, and that is this the result of that here this experiment. Electron behaves like the wave, and that was postulated by de Broglie hypothesis. Also Davission and here this Germer calculated the wavelength of the electron here this beam. Now that is this experiment, we have to go in detail as we know what is the principle. The principle which we mentioned earlier, if the electrons are in the motion, once they diffracted from the nickel crystal, that electron behaves like a wave nature. And that experiment, that here these terms, experimentally we have to prove by using this polar graph as well as the theoretical value. If both results are same, then finally we say that it is in good agreement with the theoretical result. And it confirms the de Broglie this hypothesis, that is electrons behaves like a this wave. Thank you.